lecture of Professor Tim Eifler at the University of Arizona, and one of my supervisors. So have fun, and if you have questions on Cosmology, etc., talk to us later, and write questions for the discussion. The discussion yesterday was great.
Sure. All right. Welcome, everyone. After the lunch break, I hope you did not eat too much and you're not that tired. This is the second lecture from Models to Data. So yesterday, we started concepts of data analysis and in the specific context of cosmological surveys. But we didn't go through the whole lecture. There is still a lot to discuss. And actually, we ended right at the point where I was going to talk about systematics. And so I just decided to restructure the lecture today. We're going to do mostly systematics. And there is no better topic to talk about systematics than to go into the nitty-gritty details of weak lensing. So we will cover systematics in an abstract way first, and then actually go into some details of weak lensing. But first, so homework-wise, I mentioned this link. There is a zip file that you can download. It's roughly this size. And then there should be a README instructions that allow you to install Cosmology. And we will have one lecture. It might not be in this room. It might be in some other room, where we will actually work hands-on trying to reproduce some of the plots that are in this science requirement document, basically doing a simulated analysis of LSST. But just quick question, who has downloaded this already and who has tried to follow the README? Okay, wow, very nice. Who has successfully followed the README? Wow, so it can be done. This is a clear success. I want this on the record. No, okay, so even without any further help, because the README was something I wrote and I was not sure if that actually would work for everyone. Who has had problems here installing this just based on the README? Okay. It's much fewer also on the record, but yeah, I'm very happy to talk later one-on-one on how to install that with this very specific problems. Okay, quick recap. This is a problem we're discussing. This is data. This is theory. These are our models. We want to try this connection. We want to make this connection. Yesterday, we discussed what are the, wait, let me see. What are the relevant ingredients? And we basically took apart this equation-based theorem and looked at what is the posterior probability of a model given the data, and it is computed by the likelihood function of the data given a model times some prior information that you have. And then there is some normalization constant. That's only important if you want to do model comparison. If you go into it a little more details, this is a good slide to envision what is actually going on. So real universe, instrumentation, detector physics, then you get this very nice image, more or less very nice. It has all the artifacts on it. Then you pipe this through an enormous amount of software, which does object detection, does all sorts of image processing, which does astrometry for all these objects, photometry, and if you're interested in weak lensing, also shape measurements, etc. You process all of that, you get a catalog. From the catalog, you compute a summary statistics, and we've discussed what summary statistics are. Some of those that are, or some summary statistics that are mostly used in photometric cosmological surveys today are two-point functions. But there's other summary statistics as well. And from the theory side, you start out with a cosmological model. You have some certain parameters. You generate initial conditions in a numerical simulation. You let gravity evolve this setup, and then you get this nice dark matter filamentary structure. You populate it with galaxies to the best of your ability. That's all model uncertainties. From here to here, that's relatively safe. We kind of know what gravity does. From here to here, that is very, very not safe and highly uncertain, because galaxy formation is an important topic just in itself. So, and once you have this populated numerical simulation, you can also generate a galaxy catalog with the relevant properties, with galaxy shapes, with galaxy colors. And from this catalog, you compute the summary statistics, and then you have a measured summary statistics. you have the ability to predict a summary statistics as a function of the model, and you do the likelihood analysis. And that was the final slide that we discussed yesterday, putting it all together. What are the ingredients of this likelihood analysis? What goes into Bayes' theorem, into the different parts? Independent probes can enter as priors. And then we have this likelihood function. And what are the main ingredients of the likelihood function? Well, first of all, modeling the data vector, so the so-called model vector generation as a function of parameters. Then we need the covariance matrix that tells us the uncertainties on our measurement. And then we also need to know what is the functional form of this likelihood. And it's been suggested that that should be a Gaussian. And given that we have a high-dimensional data vector, a multivariate Gaussian. But it was also mentioned that that is not necessarily the right functional form for this likelihood. There are other choices to be made, or there are other choices that should be considered and that have been considered in the literature. For example, in case of the CMB, on very large scales, that is an inverse Wishart distribution. Okay, that was yesterday's lecture. You are all familiar with these participation forms. Please just take one out. Just take a piece of paper out. And I wanted you to discuss, and we've mentioned this yesterday as well, there's two broad categories of uncertainties or errors that enter cosmological data analyses, but generally that enter data analyses of all kinds. No. What are these broad categories? How can they be separated? So if you go back to this slide, here in the covariance matrix, there's a certain type of uncertainty that is modeled through the covariance matrix. But it is not all the uncertainty that exists. There is other types of uncertainties as well. And they can be usually categorized into two main categories. What are these, broadly speaking? Okay, discuss and write something down. If you have absolutely no clue what I'm talking about, then call me and I'll come and talk to you. Who needs more hints? Who wants more hints? Okay. So there is one category that you can reduce by, is that the next question? No. There's one category that you can reduce by just observing more. The other one you cannot reduce by observing more. Not necessarily. It's not that straightforward, right? If you look at what is the mean number of eggs a chicken produces, if you just observe 3 chickens, that's perhaps not a very good ensemble. If you observe 1 billion chickens, you get a better idea. And that is a certain source of uncertainty. That is an uncertainty that has a certain name. Okay. All right. This is just 2 words, so I'm not going to wait that long. Please exchange some of the participation forms. Who would like to read, or who knows the answer? Yes.
Statistical and systematics uncertainties.
Yeah. So there is statistical and systematics uncertainties. And it is very clear how to improve on one of them. We had this fabulous chicken example. But But now I would like you to specify what are statistical uncertainties in the context of cosmological surveys. What is meant by that? How can you improve? How can you reduce these uncertainties? And then can you name some systematic uncertainties for a photometric imaging survey? Something you heard about. Sorry? And don't shout them into the, just write them down for now. Yeah. And bias is something, yeah, let me, while you're thinking about that, bias is something that is a very general word that for some reason has been stolen by the galaxy clustering community to mean something very specific. That's something I never quite understood, how they got away with that. But yes. Okay, so first this one. Think about it, talk about it, and write something down. What are statistical uncertainties? How can you improve these uncertainties in a photometric survey? So the main question, if you need one more hint, is what is the main observable that is being used in all of these photometric imaging surveys that we discussed? What's the main thing that we observe in the universe? Is there anyone who's totally lost in this? Okay. So 1 more minute, and then we'll exchange. All right, please exchange your forms. Just quickly hand them to your nearest neighbor. Okay, who would like to answer the first question? Specify, what are statistical uncertainties? How can you reduce them? Oh.
So statistical uncertainties are not intrinsic to the system. They can be reduced by amplifying the number of measurements. In galaxy surveys, for instance, one can consider a bigger number of galaxies.
Yeah. So statistical uncertainties are, for photometric surveys, mostly mitigated by observing more galaxies. There is also the distinction between observing more galaxies and observing more area. Area is also an important factor to beat down cosmic variance. So most of the noise terms, they do scale with, or the noise terms in general, they do scale with number density. But all the terms in the covariance matrix, for example, scale with area. That includes the cosmic variance term and the mixed term. And that is part of the reason why area is, to a certain extent, more important than just pure number density. However, number density of galaxies also comes with increased redshift. So you cover an increased range in redshift, and that can be important as well. So if somebody tells you area is always more important than number density, that is not true. That's only true if you were to keep the redshift distribution fixed. Okay, number 2, name systematic uncertainties of photometric imaging surveys, and how can you reduce those? And that is a much more complex question, so generic general answers are fine. Who wants to take this? I'll help with that.
There are deviations that affect a measurement shifting it in a given direction.
Mm-hmm.
So for example, if you are computing a correlation function and you have a contamination from stars, those have specific locations in the sky and they can shift in certain scales the correlation function up or down.
Mm-hmm.
So.
That's right, yeah. So that's a very interesting example. What happens if you have a contamination with stars? Say if you correct for them perfectly, right? Then they actually have zero ellipticity. That's the main idea. So you would actually decrease the amplitude of correlation that you measure if you have a too strong contaminant of stars. Star contamination is a problem. So in the DES galaxy catalog, we had millions of galaxies in of order 50,000 stars. And if some of them creep into the, well, actually it is not so bad if some stars creep into the galaxy catalog, but what is really bad is if some galaxies creep into the star catalog. Do people know why? You know why? Oh, okay. Well, that would be, wow, okay. Okay. Yes, exactly, because you contaminate the point spread function measurement. Point spread function is measured by stars, and if you mistake a galaxy as a blurred out star because of the atmosphere, then you screw up your point spread function measurement, and then that affects your entire weak lensing measurement. Yes, okay, sorry.
So when you say that it's normally better to cover a bigger area of the sky, but it's not really true when you are considering the 2-point correlation function, right? Because it's better to stay longer in a place than going to in an area than going to another area, because you're losing some information that you could gain by staying the same point and having more points in your 2-point correlation function. You understand?
I mean, the number of pairs is the number of pairs is actually the important ingredient here that you have. The reason why you want to cover a large area is because the dark matter structure induces correlations over very, very large scales. And so you do not just want to stay in one patch because it will not resemble the overall universe. So you could end up with observing a small patch of the sky that is very heavily biased because there is just a filament along the line of sight. And that's why you want to go wide. So even if you were to go very deep in this small patch, right, you would actually have a biased measurement. It would not resemble how the universe looks like. Okay. There's a famous case, the Cosmos field. Cosmos is an incredibly deep cosmological observations in many, many different bands. There's only 1.6 square degrees in size. DES is 5,000 square degrees. So the Cosmos area is a known overdensity. There is a large filament that's kind of known that is an overdensity. So if you were to assume that from that small patch of the sky, you could infer cosmology for the whole universe, you would be biased. You would think there is more structure in the universe than there actually is. So that's actually the reason why we want to go wide. But you are right in the sense that the 5,000 square degrees area that we use in DES, right, the correlation function, if you look at the binning, does not go to 5,000 square degrees, right? It's kind of cut off at 6 square degrees, roughly. So not even that. It's more like 4. So that it is true that we do that, but it is still worthwhile to observe these 4 square degree correlation function over many different patches in the sky. And that's why you build up area. Okay, those are very good questions. Forgot where we were. Oh, systematics. Yeah, excellent. You had the example of galaxy star contamination and PSF. Perfect. Are there other systematics that people quickly want to mention for photometric surveys? Yes? Sorry, say again? 0-point error for photometry. Yes, that affects photo Z errors. Anything else? Yeah, so shear effect is not really a systematic. No. So shear calibration. Did you say shear calibration? Okay. So how well can we measure shapes? Yeah. And magnification, that is an astrophysical phenomenon. That is a systematic. We have to account for that. And there's other systematics that are astrophysical in origin. So stuff that is in the universe itself. And we just have to have a precise model. But if we don't model it, then we have a systematic. And famous ones are intrinsic alignment, and we'll get to that, and also the fact that we have baryons in the universe, that it's not just dark matter, but we have feedback processes, and we have what is called baryonic physics that actually change the amplitude of the power spectrum quite substantially. So if we just do dark matter, then we're getting a biased result. Okay, so you can relax. That was just to wake you up after lunch. Now we're going to have a look at trouble with systematics. So a systematics-free survey, you will recover the correct input cosmology and you get some nice small ellipse. That's the ideal case that we want to have. So this is going to be a conceptual problem, a conceptual description with systematics. And it's exactly right that if we have some kind of a systematic offset on our observable, say on the correlation function, and I'll just take the example of cosmic shear, and we've already mentioned that the correlation function is psi plus minus, which is a function of angular separation and redshift. So if this actually has this always has an uncertainty that comes from not measuring shear correctly, and that is from not measuring shapes correctly, and that uncertainty is usually parametrized with m. So this psi goes over to something that is psi. Well, I'm not going to write that out, times 1 plus m, usually squared. So this parameter describes an uncertainty. It's a systematic uncertainty and describes how well can we measure shapes in weak lensing. Now, if we don't account for this, we get a biased result. We'll end up here, although the true cosmology is down here. So what do? Okay, you go and you measure m in some simulations, right? You have to correct for this somehow. So you correct for it, and you bring the ellipse back. But also, you know that however you have been able to determine m, you don't know m precisely. Right? There is an uncertainty in that. If you ran some simulations on testing your algorithm, how well can you measure shapes, you will still have a residual uncertainty in this external derivation of m. And that uncertainty causes the ellipse to become larger. You have to account for this uncertainty in your likelihood analysis. And usually adds a dimension to your posterior, to your sampling problem, and that will cause the ellipse to increase. Sorry, wrong way. Now, you can say, okay, this is now degrading my measurement a lot, and I don't want that. I really don't like that. So I'm going to run some more fancy simulations to get a better handle on M. You run better simulations, or you go and you observe with a different kind of telescope, with a different data set. You do some cross-validation, and suddenly you get better information on this nuisance parameter M, and you can put a better prior on it, and that will decrease the ellipse. So this is the name of the game, right? First of all, you have to correct for biases to bring the ellipse back. But you know that this correction algorithm that you have implemented, that has uncertainties. If you say, I'm sure that my uncertainties of this additional parameters are small, you can also just say, I'm not going to marginalize over this. I'm not going to include it in the likelihood analysis. But you have to justify then that they are small. Technically speaking, every kind of correction that you do to your data has an uncertainty, and you have to account for that uncertainty. And very, very frequently, we have corrections in our algorithm where this is not really done. And usually, always, you have to justify, OK, I'm not including an uncertainty of that correction because I think it is entirely negligible. 10 to the minus 8 versus my measurement is of order 10 to minus 4. That's the justification that I would like to see for every correction that is made. I don't think that we do that properly yet. But we do it for the most important ones. How well can we measure shapes is one of them. And then, indeed, improving the priors, that reduces the uncertainty. Now, but unfortunately, if you say you have measured M, and this is your best value for the correction, M star, and you associate this kind of an uncertainty with your correction, very likely this M star is not the correct mean, right? The correct mean would mean that your ellipse is back-centered on the true input model. But very likely what the universe has is somewhere off, somewhere here. So your ellipse will still be a little bit offset. And it is important for this prior, for this uncertainty quantification to be conservative enough that the confidence intervals, that the credible intervals still capture the true cosmological model. Otherwise, you're back in kind of this exaggerated regime where the ellipse is actually too far off. So even if you correct for it, and your correction is not precise, and your error model on this correction is actually too speculative, then you will get a bias that is intolerable. Yes?
Is your prior on your schematic bias?
Yeah.
If you run an MCMC chain to correct this,
This is the correction for it.
even for the MCMC with a high deviation of your prior, you get this
Well, the
bias.
right, very good question. That is because the prior that you put, right, the prior that you put here is pushing the ellipse up, even though the data tells it to stay down.
Shouldn't the Markov change probably push it back to the right?
Only if the data is much stronger than the prior. But in Bayesian likelihood analysis, you always have priors and likelihood competing. And if your prior is too speculative, if you think, I really know this exactly, my simulations are so perfect that I know this precisely, then you might say, well, I'm going to put some really, really tight prior on this, like that, right? But the true value now is here. And so at that point, the prior actually wins against the information that you get from the data. You always have to imagine that the data has to constrain a 26-dimensional parameter space, or 70 dimensions, right? So it can only help so much with one specific parameter.
But suppose you have an infinite computer power.
Mm-hmm.
Shouldn't you be able to run a huge MCMC chain and
It-
get corrected?
It does not depend on the MCMC chain. The prior will still push it. If the prior is powerful enough, because you give it that power, that is a choice you make as the analyst. But if you give the prior that amount of power, then it's not a function of length of the chain. But we can actually test that. I have a small tutorial where you just run an MCMC chain, you give it a very strong prior, and you let the data try and find the maximum likelihood point. You can see how the prior and the data compete. And depending on how strong you make the prior will win.
How in an analysis would you have an idea that your prior distance is really too bad in your?
Yeah.
How can you see that okay, my data is not good because my prior is bad?
Right. So that is exactly the dilemma in which a lot of the analysts are, and there is no unique mathematical solution. You can run better simulations. You can you can tell somebody else, hey, you have another code. Could you also do this type of analysis and tell me what kind of uncertainty do you get? You can go and cross-correlate it with other data sets. And actually, there is a version, there is a paper that I might show a plot later. We'll probably not get to it. Where we use information from the CMB to get a handle on this shear calibration parameter M. You always have the choice to make this prior very, very broad, right? If you are uncertain, if you feel uncertain about it, make it broad and see what the data tells you. Because at that point, the data will win. But you might win with a huge ellipse, right? But then if you add in additional information, like from CMB lensing, you might recover some of that information again. So those are the choices you have: better simulations, independent checks, other data sets, and then you can validate your results. But it is a dilemma to a certain extent. Thank you. Good discussion. OK, so let's say you have this kind of result from your photometric survey, right? We already mentioned that a photometric survey has several cosmological probes: weak lensing, galaxy clustering, galaxy-galaxy lensing. There's supernovae. There is, actually, I have a slide on this. There is supernovae. There is CMB lensing, etc. And the first step of such a likelihood analysis, when you want to do a multi-probe likelihood analysis, the first step is always you look at the individual probes and you see, do they agree? Because you should not combine stuff that does not agree. Then you'll just get something in the middle that is kind of meaningless. So the first step of such an analysis is always, do they agree, and can I combine them? And so what do you do if you get something like this? And I would like you to think about that in a group again, and to come up with a solution. What would you do? What are your suggestions if you have a DES analysis and all the individual probes kind of disagree? Think about it. This is a hard problem, and it's mostly a slide where I want you to think about how you would handle this. There is no mathematical solution to this. It's a strategy question. You'll have to talk about it with people. So this one you don't have to write down. Just talk about it, and then someone in a group will represent the result of your discussion. I'm trying to get them to, otherwise they will fall asleep, I think. Yeah. Excuse me?
My answer is very simple.
Oh, what, new physics? It's neutrinos?
Trust the CMB. Trust the CMB. Give me more money to build a new CMB experiment.
So give me more money yeah.
I start with my answer? So my answer is give me more. So people are tense.
I don't think they're tense. I think so.
Because this is a difficult question.
Yeah, it's a very difficult question. Yeah, I agree. It's okay. So I wrote down some questions to guide your discussion, but you don't have to follow them necessarily. There are some questions that are useful, perhaps.
And I'm gonna eliminate the trivial answer, which is trust the CMB or give us more money. So
There's no cynical answers here. There's real answers.
although the first one is on my heart.
Okay, now continue talking. I still should talk. It's okay. This is hard, so I want them to talk about this a bit. What?
This is not far from reality.
What do you mean? This is. No, it's not part. Yeah. Also, the size of the ellipse do not reflect my preference.
That's okay. But
Yeah. I think it's important for them to. I also very much like the question about doesn't the data tell you whether it's wrong? I very much like the question about doesn't the data tell you whether it's wrong? What is the right value of m? If you run the chain long enough, right? Yes. Oh, great question.
Are 1 sigma?
Yeah, let's say they're 1 sigma. Yeah.
Because I was like, if we don't have any information on the, like, it could be like 0.1 sigma. And
Oh,
like
okay. No, right.
Sigma, they're intersect or something like that.
Yeah, let's say they're 1 sigma then. Yeah. 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 Yes, so very good question. What is the sigma level of this? Is this 0.1 sigma? No, this is not a trick question. This is like, let's say this is a 1 sigma thing. So these ellipses here are to indicate that these probes are discrepant, actually. They are toy depiction of a discrepancy. Yeah. Yeah. Yeah, okay. So who would like to speak for their group and quickly come up with either some answers to those questions or say something how they would proceed? It's very unofficial here. There's like no grades. There's like, I'll do a lot of the talking anyhow.
Come on. You look at me. No?
Yes, come on. That's fine. No. Okay. Okay, perfect.
So I think the possible explanation for this is you first, or you have unknown systematics, or your model is really wrong. So yeah, I guess it's the second one because you have galaxy clustering and galaxy clusters that, in some sense, they are related to the same physics. So you should expect the same result for your cosmological model. I think so. You can combine these proofs, but it doesn't mean anything. It doesn't make any sense because they are in complete disagreement. And a strategy to find a solution for this is uses another model or something like
Another
this.
model?
Another model, yeah, another cosmological model.
New physics?
New physics, yeah.
You're saying this is an indication for new physics?
Yeah.
All right. Yeah, there were, yeah, very good. No, there were lots of really good thoughts in this. Yeah, I'm going to say something now, and then perhaps some other group could also say something. Yeah, so one very good idea was to look at which ones of these should actually be consistent, right? And which ones of these are independent. So supernovae is kind of independent from most of the others. It is very far away. And you can look and check, well, should galaxy clustering perhaps in principle be similar to galaxy clusters? But even though the underlying physics might be somewhat similar, it still comes down to what is the exact redshift binning that you have assumed for your galaxy clusters, right? What is the exact redshift binning that you have assumed for your galaxy clustering? Because if those are sufficiently different, for good reasons, mostly for measurement reasons, right? Galaxy clusters, they're usually optically detected by red mapper. Red mapper only goes out to redshift of 1. So you're not going to, even less. So you're not going to include any clusters beyond redshift of 1. Whereas for galaxy clustering, you will go to higher redshift usually. So there's these kinds of ideas that can cause stuff that is affected by similar physics still to be discrepant, right? But it is still a very good thought to look at which ones of these kind of probe similar physics. Something else is, you said you can't combine them, and that's true for most of them, but you might be able to combine these two, right? So there is some of them that are actually close enough that you have to investigate very clearly. Are they really in tension? Is it significant? Or can I perhaps combine them to get something that is more stringent, and then I can say, okay, these three are different from the others, and then I look at what's going on here, what's going on there. There is perhaps an argument to be made that if there's that three independent, more or less independent probes, give some more credibility to this. I forgot what else I want to say. Strategy, yeah, right, you said new physics. So new physics is, so it is absolutely correct that if you find discrepancy in a multi-probe analysis, right, you can find new physics in many different ways. One is discrepancy in the individual probes, and the other is if you combine them, if there's not a discrepancy and you combine them, you get very, very tight constraints on your physics model, and you might be able to say, I falsified lambda CDM or something like that. But I would never really jump to new physics. I would first say, okay, very likely there's a bug in my analysis code, and I'm going to look for bugs. Or I would say, well, somebody didn't model shear calibration right, and it is affecting at least these two. Or I would just go photo-Z. Photo-Z are the culprit. That would actually be my main suspicion. So systematics or new physics is the question, right? And new physics, I guess, if you want to claim that, that's a hard thing to do in the presence of all the systematics. So yeah, but is there some other group that wanted to? Yeah. But yes, thank you very much. It was really good.
And also, there is the fact that some of them rely on priors coming from the CMB, and they're all like relying on the same priors, right?
Well, okay, so here I was thinking that they are actually independent. You're talking
They
about
are-
if I have added in some other prior information.
Yeah, they're based on the same, relying on the same priors. I don't know how to further.
So in DES and in all the other surveys, there's always two types of analysis. One where you first do only DES or only kids, and then where you do DES plus Planck, right? You add prior cosmological information to your data set. You are still right in the sense that there are priors on many of these parameters still, but not really on the cosmological ones. The cosmological ones are usually free of priors, more or less. Okay, are there any more thoughts about this? What would be, yes, Vivian?
But if you're that careful when they disagree, but when they do agree, you jump right into lambda CDM is correct. Are we biases? Like every time they disagree, we overly check. Every time they agree, we just accept.
Yeah, that is a danger. There is that's the problem of a stopping criterion in an analysis, right? When do you stop the analysis and when do you say now it's good enough? And frequently, people don't stop if they find something like this, right? This is where they start searching for systematics, where you dig deep into your photo Z code and where you actually find bugs. And if you, for some reason, and that's the next slide, end up somewhere near the Planck, then you say, okay, no, I'm good. I've done everything right. I'm good. And that brings you to the matter of null tests. Null tests are really important. It basically means you have to come up with a series of tests to validate your experiment. And it means that you can only, and that's a different topic, unblind your data after your data passes all of these null tests. And these null tests should be defined before the experiment. You have to think very hard before the experiment. What are the tests that my data has to go through for me to say, this is now a credible analysis, right? If you do this afterwards, then you will always be biased because you will do it more thoroughly if you are, like here, weak lensing away from Planck. And the supernova people, they're probably going to say, I'm fine, we're good, we've done everything right, right? So they're not going to check their light curve modeling and what else they do. So it's the question of a stopping criteria, when do you stop the analysis, is a really important one. And designing your suite of null tests before is really important as well. So, okay. Anybody who wants to say anything more on this topic? There's still this question. Does this influence your result if you are close to Planck? Should it influence your result? Yes?
I think yes, but it shouldn't because it should because this is human bias, right?
Well, it depends on what exactly does it mean, does it influence you, right? So obviously Planck would be another data point, another ellipse in this overall realm, and it is one that has to be considered carefully. But it should not influence you in the sense that, okay, DES supernovae, they're good, and DS weak lensing, whoa, you never understood photo Z's. That is not the choice to be made. Okay, all right. Now let's talk some real systematics. This was a bit abstract. And as I said at the beginning, there is no better topic to talk about real systematics than weak lensing. And Rogerio pointed out that there was not yet a weak lensing lecture in this school, possible. So I thought I would say a few words on weak lensing, but it is not a thorough, in-depth lecture. And we'll see how far we get today. This is the weak lensing landscape. There's two very good reviews that you can read if you're interested, especially the first one has all the relevant math in it. The second one is a bit more recent. This is by Peter Schneider, 2005. This is Rachel Mandelbaum, 2017. There's many others. Henk Hoekstra has written a very nice review. So there is no shortage on weak lensing reviews if you're interested in the details, but this is going to be a quick overview. So the weak lensing landscape, basic concepts of lensing, cosmic shear, shape measurements, photo Z's, And after photosys, there is always this small detour. Why do you still want to do weak lensing? And then there is astrophysical systematics, intrinsic alignment, baryonic physics. And after you've dealt or after you've explored all of these systematics, you usually end up with, okay, I'm not just going to do weak lensing. Now I'm going to do multiple probes because that helps a lot with some of these systematics. Okay, so this is one history slide. In 1915, there was the development of GR that allowed Einstein to actually predict the bending of light through massive objects precisely. And he predicted that there would be a difference by a factor of 2 compared to if you were to predict the bending of light of such an object with Newtonian gravity. Now, you might say, okay, how can I predict bending of light? Light is massless with Newtonian gravity. You can. It's actually a very nice calculation. The mass cancels out, and you actually get a value for the deflection angle. So this can be done classically, but in 1915, Einstein said, look here, my theory predicts something that's different by a factor of 2. And the idea was that a star that is actually behind the sun will be visible will be visible even though the sun is in the way. So you have the problem that the sun is very bright, so you can't observe it. They waited for a solar eclipse. And then there was a British expedition to the island of Principe in 1919, sorry.
100 years, but that's wrong.
What's wrong?
Because there are 2 expeditions.
Yeah, there were 2. I know that.
The best pictures are from Brazil.
Yes. Of course. Yeah, I'm sorry. Wow, I should have really checked that. I should have really checked that slide. Yeah. Yeah, I'm sorry that I'm going the British way here. It's true that I did hear the story that some of these pictures and some of these measurements were a little bit fine-tuned to actually prove Einstein was right. So it's unclear if.
That's not right, because they did a reanalysis of the same pictures later, like the 70s, and it was correct.
It was correct. Okay. So.
I can show you.
Okay.
Because there was a big celebration this year, because it was 100 years of this.
Yeah.
And people dig into the history of this, so there are lots of stuff.
Yeah, I shouldn't show history, I guess. This is my lessons from this. Okay. Anyhow, this expedition did check the experimental prediction, did check experimentally on the prediction and found that GR is correct, and that was a big win. And this doesn't just happen with stars that are behind the sun and where the sun acts as a lens, but it also happens with galaxies. So if you have a lens galaxy here, this is you as the observer, and this is the galaxy that emits light. You can see if there's perfect alignment, something like an Einstein ring. And if there's non-perfect alignment, you can see multiple images. And this is something that does occur if the mass of the lens here is sufficiently large. So if you have something like a massive galaxy cluster. It does not really happen in the universe as such. And those are the pretty pictures that you get. This is the famous Abell 2218. And you can see these very nice elongated arcs. You can do the same experiment with a wine glass at home. So this is kind of an ellipse from your candle. And then depending on how you have this optical lens, you can see multiple images, or you can even see an Einstein ring. So it's a very nice experiment that you can do just in your home place or restaurant. So the takeaway here really is that every object in the universe is actually lensed. And this is a depiction of what happens if you have a galaxy field without lensing. It's just a toy simulation. And then if you turn on some exaggerated version of lensing. So everything in the universe is lensed. And why is that? Just a quick question. Why is everything lensed? There's not a cluster everywhere. Yeah, so there is always a change in the deflection potential. So a change in the potential everywhere. There's always a gradient, and that is what causes lensing. And it is not strongly lensed, but everything is somewhat lensed. And it is because of the large-scale structure that is just between every object, at least, yeah, between every object and us. Okay, so those are the very basic concepts of lensing, and now we're talking about a specific version of lensing, and that is cosmic shear. And you've seen this plot already, but I like to show it because it so nicely describes the concept. Faint background galaxies that are far away from the observer. So those are at redshift, well, 0.1 and higher. And for most astronomers, actually, this is considered far. Not necessarily for cosmologists or people who deal with the CMB. It goes out to the lensing, or the highest redshift bin for, say, W first is somewhere at around redshift of 4, one of the deepest surveys. Okay, so faint background galaxies emit light. Light gets deflected and distorted in the gravitational potential of the dark matter structure. And what you see here is a slightly distorted image of the galaxy. So, I mean, we deal with galaxies because that's what the universe gave us. Not all of them are nicely elliptical, but all of them are somewhat lensed. And so then you observe many millions of these galaxies. And these galaxies, you can measure the ellipticities, and from the ellipticities, you can measure the shear. And the shear field tells you the statistical properties of the shear field. They reflect statistical properties of the dark matter field. It's a projected quantity thereof. Now, you have lots of difficulties. In reality, you have something like bad seeing, PSF anisotropy. You have tracking errors. The telescope tracking is not known precisely. Bright objects, pixelization. You have noise, blending, intrinsic alignment, baryons, etc. Nonlinear density evolution, photo-Z errors, shape calibration, and so on. So in reality, this is very, very difficult. But in theory, this is relatively straightforward. This is a depiction of the galaxy field. This is if you knew where the dark matter is, and you can see that these align not randomly, but they have some preference that comes from this projected filamentary field. Okay, now what does weak lensing actually, or what does cosmic shear actually do? Well, we talked about two-point correlation functions, but how exactly are these two-point correlation functions calculated? So you have two galaxies. That is a two-point statistics. You find what is the center of these galaxies. How do you find that? You look at the light profile. Where is the center of the galaxy? That is based on the light. And then you draw a connecting line between these two centers of the galaxies, and you define your coordinate system with respect to this connecting line. So this is a unique definition, right? Center of the galaxy, connecting line, and then you have two components, two ellipticity components. The ellipticity component that is, this is dying, the ellipticity component that is tangential to this line, and the one that is 45 degrees rotated. Let me try this one. Better. 45 degrees rotated. So that's, those are the two ellipticity components that you need to calculate your correlation function. So you measure the ellipticities, these two components, for your millions and millions of galaxies. And you know that the ellipticity that you measure of the image of the object that you see is composed of an intrinsic ellipticity, the ellipticity that you would measure if you could fly there, and the shear. And that's the effect that is induced by large-scale structure. Okay? That's a simple sum. Intrinsic ellipticity of the source, it's called source ellipticity, plus gamma. Gamma is the shear. That's what you observe. Now, you can actually derive that if the universe is homogeneous and isotropic, and that's what you assume, that's what we have good reasons for, and that is also an assumption that enters, there is no preferred orientation of the intrinsic ellipticity of the galaxies. They are, if you calculate the ensemble average, it would be 0. No preferred orientation to begin with. Everything that you see as a preferred orientation is induced by this large-scale structure that is between you and the galaxy field. So for weak lensing, you can actually show that the ensemble average over the observed ellipticity is the shear. But you're interested not in this. You're interested in the two-point function. So you're calculating two two-point functions because you have two components. The shear is a polar. And so you get two of these two-point functions, psi plus and psi minus, and they are a function of the angular separation angle theta. So this is just this one. It is interchangeably used as theta or var theta in LaTeX. It's kind of the same. It's the angular separation. Don't be confused by that. It is a function of this separation, and it is also a function of the tomographic redshift bin, and we'll get to that a little bit later. But then you calculate these correlation functions just by gamma t, plus minus gamma cross. And actually, because you can't measure gamma directly, this is where you have the ellipticity. So ellipticity tangential times ellipticity tangential, ensemble average, and then the cross components as well. But the ellipticities cancel out in this calculation, and you're left with the shear. So what the correlation function actually measures, the ellipticity correlation function, what that actually measures is the shear correlation function. And that's how you obtain your observed data vector, psi observed. Actually, this psi over here is my psi. Psi is a very hard letter to write on a blackboard, so I just, yeah. OK, that's how I get my data vector. And then from the theory side, you start out with a set of cosmological parameters. You calculate the density power spectrum, and you get the density power spectrum either through simulations or through Boltzmann codes plus linear structure growth plus halo model to get nonlinear structure growth. That's what gives you a density power spectrum. And then you project this density power spectrum, and that is the that's the projected shear field. So the power spectrum of the shear is blah, 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 lots of parameters, numbers, and an integral over redshift with some weights of the density power spectrum. And from there, from the shear power spectrum to the correlation function, that is just a Fourier transform. And this, in principle, is a way how, starting from cosmological parameters, you can get a prediction for your observable. So on the last slide, we've just seen how to get your observed data vector from the catalog. You just do this for 10 billion galaxies. You get your psi observed. And this is how you can predict the correlation function. And there's different ways of doing it. And then you compare data and model in a likelihood analysis. So that all sounds relatively easy. Now, we've mentioned tomography already. Tomography means that you bin your overall redshift distribution into many different bins. So let's say you have a galaxy sample that gives you a redshift distribution as this red line. And this is actually something for W first that was taken from the Cosmos field. So you get this redshift distribution, and now you say, OK, I want to separate it into 10 bins. And so you separate your source sample into 10 different bins, and they're smoothed out because there is some uncertainty in this, in the photo Z process. So they can overlap. That is possible. But those are now your 10 different bins. And in DES, this is the redshift distribution. You can see how much they overlap realistically. We had 4 of these. And now you can actually see how does the lensing integral evolve if I pick different source samples over here. And you can calculate what is called a tomographic correlation function as a function of one bin. You correlate galaxies in one bin with galaxies in a different bin. And so say you have 3 bins, you get a correlation function psi 1, 1. This is an autocorrelation where you correlate galaxies in one bin with the other. Psi 1, 2, where you correlate galaxies in bin 1 and bin 2, and so on. Psi 1, 1, 3, 2, 3, and 3, 3. So altogether, you get 6 different correlation functions. This is what, well, if you have 4 tomographic bins, you get 10. That's what we had for the DES analysis for the cosmic shear signal. And again, because there is psi minus and psi plus, altogether you get basically 20 different bins in redshift. And then you have the theta bins again in arc minutes. So that's how the data vector is composed. And we've discussed that already in the last lecture, roughly. OK, shape measurements. I'm going to go through a couple of slides to explain what actually happens here. This is how the galaxy would look like if you could fly there. This is an exaggerated amount of shear, 20% shear, that does usually not exist. That only exists in the proximity of very massive clusters, but does not really exist when you look at the large-scale structure lensing. It is not a 20% change in the ellipticity. It is more like 1%. But okay, if you could fly there, the intrinsic image would look like this. Sheared, then it looks like this. But unfortunately, you are below the atmosphere. So you observe something like this. Really not as pretty. And unfortunately, you also have something that is pixelization. So now your image more or less looks like that. Depends on the pixel size that you have. And also, you have noise. So this is it. And this is a heavily exaggerated effect, right? This is a 20% shear, and that's exaggerated by a factor of 20. So in summary, what happens here? Your very nice image gets sheared, everything's still fine. Okay, problem one is the atmosphere, next is CCD, and then there is pixel noise. So how do you reverse this? How do you actually get back to this image? This is what you would like to know, right? This is, you have no chance, but this one is what you would like to know. Well, luckily we have stars. So you have pixel noise, and stars are affected by everything, but they're not really affected by lensing. They're too close. There's nothing that lenses a star. And you know that stars, for us, are supposed to be point sources. So we can just reverse all of these steps, and then we know what all of these individual things do to our very, very nice galaxy image. That is PSF deconvolution. That is accounting for noise and accounting for pixelization. And it might seem straightforward, but it is really not, because you have to imagine that this is a position-dependent effect, or most of these are position-dependent effects. And you don't really have a star always right next to a galaxy. So the stars have a different distribution. There's fewer of them. So you have to start some interpolation process of how does this effect look like across your field of view. And then you correct for that approximately, but not precisely. And so this uncertainty is actually what is being captured by this parameter m, is one of the effects that is captured by this parameter m that later enters your likelihood analysis as an extra dimension. It's the question, how well can we measure shapes? And this is a connection of artifacts in the data, and they're being accounted for by an extra dimension in your likelihood analysis. Right, I'm not sure if I'm going to do that. Okay, this is something just to think about. Let's not do that right now. But so when I wrote this talk, I was thinking about, should I include how do we actually exactly measure the shape of a galaxy? This has actually changed quite a bit in the past, and there are some very fancy methods out there. Previously, it was relatively, well, theoretically, it was straightforward. You measure the quadrupole moment of the brightness distribution. You have an ellipse, so quadrupole moment is useful. Second order moments of the brightness distribution. And you apply the shear equation. You have an estimator for an ellipticity. But nowadays, there's a lot of model fitting going on, and you have a model for the brightness profile of the galaxy, and you try to fit that to the best of your abilities. You can calibrate it with simulations, etc. So that's something to think about, but I won't go into details here. I wanted to put things into perspective. So this looks very nice, just to recap, right? All very pretty. But if we now look at the actual data, this puts things into perspective quite nicely. So this is a typical star that is used for finding this PSF kernel. And this over here is a typical galaxy that we use for a cosmic shear analysis. So to all the theorists in the room who want to use weak lensing at some point to do, I don't know, neutrino physics, modified gravity, etc., keep this in mind. It can be done, but it is important to be aware of it. It is important to keep it in mind, right? You have to know that you have to be able to ask the people who've done the data reduction, what is your prior on M? Because this enters your likelihood analysis together with your neutrino parameters, together with your modified gravity parameters, and it will change your result. It can change your result quite drastically if the prior on M is large or small. So getting a good handle on these kinds of artifacts is going to be important for physics. And that's the only reason why I'm really doing systematic stuff most of the time. Right, okay, we're moving on in the landscape, leaving shape measurements, going to photometric redshifts, land of the unknown. All right, photometric redshifts, we've already discussed that, or there was I think we've already touched it a little bit in the last lecture. So, right, when I asked what is a photometric survey, exactly. So photometric survey means you observe the same object in many different bands. And many here means for LSST 6. And this is what you would get if you could actually take a spectra. So this is the SED, the spectral energy density, the spectral energy distribution, energy distribution of such a galaxy. And you can see how this changes as a function of redshift. And you can see how the amount of flux that you get in the different bands also changes as a function of redshift, right? So a galaxy that is at redshift 1, you will see, okay, lots of flux in all of my bands. Okay, redshift 0, sorry. There is nothing here in the U band, or there's less here in the U band. If the galaxy is at redshift 0.4, you will see, okay, there's still lots of flux here, but already here in the, what is that, G? Yeah, G band, there's already less. And at higher redshift, then it falls out of the R band already. So this is how, with only 6 filters, with only 6 bands, you try to approximately assign a redshift to a certain galaxy. You can immediately see the problem. These SEDs, they are different from galaxy to galaxy. This is for an elliptical galaxy that is well behaved. But if you have a spiral galaxy, if you have irregular galaxies, you have all sorts of galaxies. So suddenly, again, galaxy formation and galaxy physics enters this very crucial ingredient for your physics experiment. And that is, again, an uncertainty that needs to be accounted for in a likelihood analysis. And it is a bit unclear how to parameterize that uncertainty. So there is not, for shear calibration, this multiplicative uncertainty. There's also perhaps an additive component to your correlation function that is being included. For photo-Z uncertainties, people sometimes use, I'm going to go to the next slide here. People sometimes use something like a shift parameter of the overall distribution. So they allow for variations. They allow for this overall shape of such a distribution to shift a little bit to the left and a little bit to the right. But you could also imagine that there is uncertainty that actually broaden the distribution. That would be a different parameter. And where does this enter? Well, it enters exactly in the measurement of in the correlation function. So in the modeling of the correlation function, where you enter the redshift distribution, that's also where this uncertainty parameter would enter. And so whenever you model this, whenever your MCMC goes to a next step, it will also predict a different correlation function because it will jump to a different parameter value for the shift parameter or for the broadening parameter. And then there is something worse that can happen to photo-Zs other than just shifting a distribution or other than just broadening a distribution, and that's called catastrophic outliers. And I'm not going to go into details, but it is, well, let's go into details. So this is a plot where you can see the spectroscopic redshift, Z-spec, versus the photometric redshift for some experiment that is somewhat like LSST. So this basically tells you where is the galaxy truly, and this tells you, or where is the, well, this actually just indicates the probability of outliers. Okay, so for galaxies that are in reality at redshift 1, this is yellow, so this is a very high value in this plot. They are truly at very, very low redshift. And that's, there is reasons why these galaxies that are truly at redshift 1 are sometimes in photo-Z surveys mistakenly put at very low redshifts. That's related to SEDs and to the filters at hand in LSST. And similarly, for galaxies that are truly at very low redshift, there is a high probability that you would accidentally put them at very high redshifts. And that is called a catastrophic outlier, because what happens is that if galaxies that are at low redshift, there's very little lensing going on. But if your model puts them at a high redshift for some reason, then you would assign a very, very large lensing signal to that particular galaxy, and that will have a large impact. So if you're saying, okay, it doesn't matter if I get 1,000 galaxies wrong in my sample of 10 billion galaxies for LSST, it does matter. These catastrophic outliers, very few of them already, can really bias you significantly. And that has not yet been taken into account in at least DES, but also, as far as I know, not really in KIDS and HSC. Okay, so two effects: shifting of redshift distributions, broadening of redshift distributions, and the second one is these catastrophic outliers. And you can only get a handle on them if you have better spectroscopic samples and if you have narrow band photometry. All right, why still weak lensing? Next slide. Just very quickly, it's a very simple answer. It's extremely powerful to constrain cosmology. The forecasts kind of, or the predictions kind of agree in that regard. This is an older one, Dark Energy Task Force, Figure of Merit, 2006. You can haunt people with this. But this is a very simple plot. If you show it to funding agencies, gravitational shear is very powerful, supernova is less powerful, galaxy clustering is even less powerful. That has changed over time, now that we understand systematics better. Obviously, we have better predictions for these kinds of things, but this is what happened in 2006. And in principle, this still holds. Weak lensing is very interesting for cosmological physics, even though the systematics are challenging. This is something that's more recent. This was from LSST, Dark Energy Science Collaboration. This is a forecast for how well LSST is going to do on dark energy, and then consequently also this allows you to say, we have to control shape calibration by that much in order to reach these goals. And weak lensing is basically the blue contour over here compared to something like supernovae, compared to something like clusters. This is 3x2 points, so that includes some kind of projected clustering and galaxy-galaxy lensing, but the majority of the information here comes from weak lensing. And I ran these forecasts, so I know that. And this is a forecast that is done for W first, and it's not yet public. But weak lensing is the dashed black contour over here. And you can compare it to the other probes that you can extract from what is called the high latitude survey. That's the imaging component of this W first mission. And this is for very conservative assumptions regarding weak lensing systematics. So weak lensing systematics here are treated very, very conservatively, whereas I put in some more speculative things for RSD and BAO, because the people in W first who were leading RSD and BAO wanted those choices. But the weak lensing forecasts, the systematics that went into this, they came from Chris Hirata, and people who know Chris Hirata know that he is very precise and conservative with respect to these systematics. Okay, so that's the reason why weak lensing is still very, very interesting. It's just extremely powerful for cosmological physics. Intrinsic alignment. Now we've reached the realm of astrophysical uncertainties. So not just nothing that is directly related to the observation and that needs to be modeled later in the likelihood analysis. This is what goes into your immediately into your prediction codes. So what is intrinsic alignment? There's two types of intrinsic alignment. So first of all, let's just quickly recap. One of the main big assumptions of cosmic shear that we had was that the intrinsic ellipticity of the galaxy does not have a preferred orientation, right? Intrinsically, there is no preferred orientation of the galaxies. But is that really true? Because we know there's dark matter filaments of galaxies that are at the same redshifts, and the galaxies that are at that redshift, they will align somewhat with respect to this filamentary structure, even though if there's no lensing involved, just because the dark matter aligns them. And that's what's called II. So here you have the dark matter blob in the middle, and this is the intrinsic ellipticity of two galaxies. And you can see that they are somewhat aligned. So the assumption that galaxies are randomly oriented to begin with is not necessarily correct. And the question is, how important is this? Turns out II is not that important. It's like 1-ish% of the cosmic shear signal. But then, and that was discovered a little bit later, I think 2004, there's another alignment effect, and that's called GI. So if you have a galaxy that is, if you have a galaxy that is at, that is at even higher redshift, G. Right, there we go. This is a galaxy at very high redshift. And this is at lower redshift, you have the dark matter plot and you have the other galaxy. Then you know that this dark matter blob does two things. First of all, this galaxy is going to orient itself towards this dark matter blob somewhat. And this galaxy, which is at higher redshift, that's going to be lensed by the dark matter. And that induces a correlation between two galaxies that are at different redshifts. Here, the galaxies are at the same redshifts. So you could, a simple strategy would be, well, let's just exclude all of the autocorrelation redshift bins, right? We're done, no more alignment. But no, even galaxies that are at different redshift, they are correlated because of this dark matter blob. It orients this one and it lenses that one. So you get a correlation, actually you get an anti-correlation here, and that effect is stronger and more worrisome, more of order a couple of %, perhaps even 10. Here, these are results of a forecast that we ran in a paper 2 years ago, also again for LSST. We made different assumptions about which galaxies to include. There is a luminosity function of galaxies that's actually quite important for intrinsic alignment quantification. There is a nonlinear alignment model, so also what specific alignment model you assume makes a difference. But this is the game that we played. So you start out from no intrinsic alignment and you end up with a black ellipse. If you contaminate your data vector with some intrinsic alignment, you actually end up with your ellipse being relatively far away. It's very close to the comic that I showed before. Now, okay, you know intrinsic alignment exists. I have to include it in my model. And here in this analysis, we included a 17-parameter intrinsic alignment model. So we modeled the luminosity functions. We gave that uncertainty. We modeled the amplitude of the alignment signal. That had an uncertainty, et cetera, et cetera. And you marginalize over all of these 17 parameters. So you end up back on top of the input model. That's all fine, but you have lost some information. So this is one way how to mitigate intrinsic alignment, but what if the universe does not correspond to the nonlinear alignment model? What if there is a different alignment model? And yeah, I should say that that is a topic of active research, looking into different intrinsic alignment models, in implementing these models into numerical simulations and propagating it all the way to data vectors such that they can be accounted for. Okay, baryonic physics. I'm not going to get through this, but I'm quickly going to describe the effect, and that's nicely done on this plot. So summary statistics of weak lensing, let's focus on the right-hand side over here, is the 2-point statistics. It is the shear power spectrum, for example. And shear power spectrum is a function of angular separation, but the power spectrum is a function of L. So this over here is large scales, large theta, small l. This is very, very small scales, small theta, but large L. And you can see the uncertainty that is indicated here as a gray area that comes from our inability to model baryons precisely. And you can see how it increases as a function of L. So on small scales or on smaller scales, there is more uncertainty with respect to baryonic physics. The black line here is a dark matter only power spectrum. And this region of uncertainty is spanned by hydrosimulations, so by simulations that include baryonic feedback processes. So those are not just dark matter particles and then gravity on top of them, but these are actually simulations where an AGN goes off from time to time, and it redistributes the baryonic matter, and then the dark matter follows because of gravity. There is supernovae that go off in these simulations. There is enhanced cooling that happens because of baryonic processes. So all these physics processes are in these simulations, but they have a huge uncertainty in themselves. The simulations don't really agree. The recipes are different. What's called, so basically the baryonic physics description that goes into them, that is, the community has not yet agreed on how to model AGN feedback, for example. So you have a range of simulations, and that range causes that we don't know exactly what the power spectrum is. The range of uncertainty is exactly this. So this is a simulated analysis for DES, or this is a prediction for DES, what the range of uncertainty is. This is for something that's more LSST and Euclid. And we have to account for this uncertainty as well. And I think I'm going to stop here. In the next lecture, I will quickly describe how we account for baryonic uncertainties and perhaps talk a little bit about simulations. But mostly, I wanted to start installing this and running some simulated likelihood analyses for LSST next time. So let's do that on Thursday. Thanks. Oh, there's questions. I always forget that there's questions.
There's questions.
Okay, good.
I have a question about that.
Oh, okay, sorry.
So those different lines are different redshift beams?
Where are we going? To the...
Yeah, this one. This different...
On
the right?
Sorry. Yeah, those are... that's correct. So this was a 10 tomographic or just 5? So these are autocorrelation redshift bins going from... Why is that not on here? Okay. This is the lowest redshift bin. This is the highest. I think this is Z11. This is Z55. So it must be 5 tomographic bins. Yeah.
Okay. Thanks.
Few plots depressed me more than this one.
Really?
Yeah.
Why?
Because there's a lot of variation between simulations trying to simulate the same thing.
Yeah.
And second, these variations are like tens of %. And we are, that means cosmic variance is like sub% is here.
Okay, this is a very good point. Sorry, I should have made this clear. These simulations don't all try to model the same thing. There are some simulations that include AGN. There are some simulations that do not include AGN. This is a suite of simulations. So the OWLS simulation, overwhelmingly large simulations, I think. They're not that large because hydro simulations are not that large. Dark matter simulations are cheap. They're large. Anyhow, this is, or at that point in time, what was the best on the market. They try to span the range of uncertainty. Sometimes they're a little bit duplicative in the physics that goes into them, but those are not necessarily the ones, they're not trying to do the same thing. But it is still a realistic assessment of the spread in uncertainty that we have to model baryonic physics.
Which percentage AGN,
Yeah, so AGN is this one. Strong AGN feedback, that is the largest outlier. So the low curve over here, that is the simulation that has a strong AGN feedback, and you can see how it suppresses clustering power. It's simply because if an AGN goes off, it distributes matter, it smooths the matter density field, it removes clustering, and so the amplitude here will be lower.
Tim, you said that you will have intrinsic alignment if you have dark matter close to the galaxies you are studying. So is this the only way you can have intrinsic alignment, or you could have other effects?
You mean like these two types of intrinsic alignment? Are they the only ones?
Yeah, you could have intrinsic alignment in any other way.
Yeah. Just trying to think. So, I mean, the reason Okay, so so there is a dependency on like what type of galaxy do you actually have. So the linear alignment model mostly applies to large elliptical galaxies. And then there is something like quadratic alignment that might be happening to smaller galaxies that has not yet really been detected very strongly. There's hints that exists, but if you would basically model these two populations independently with different amplitudes and different priors on these amplitudes. They also have different luminosity functions, etc. Yeah, so there is an environment dependence. But conceptually, the alignment would cause the same. So conceptually, these two effects would still apply. It's just that the mechanism of how do they align, that's then a little bit different. Yeah.
Okay.
Yes?
In order to be able to observe these many galaxies, we need to see the large part of sky. But then the lensing effect introduced to the shapes of these galaxies, the matter distribution in the universe between the galaxies and us also changes when we change our angular position. So I think to constrain it better, we need to look at a small point where the matter distribution changes insignificant. But then we also limit the number of galaxies to do the measurements because we look at the small size of the sky. Because while the light travels from this galaxy to us, it lens and also delens it when it passes from the voids. So what we see is the over effect, I think.
You see the integrated effect, that is correct.
Because this happens because of the distribution. So if we see a wide angle in the sky, the matter distribution also changes.
So, I mean, if you look at the sheer power spectrum, right? You have a stronger correlation on smaller scales. That is in principle correct. So if you go to larger scales, the weak lensing signal will go away. And at some point, it doesn't make any sense to look for weak lensing at very large scales because, as you say, if they are too far apart, they're not lensed by the same structure and there is no correlation induced.
So what is the limit of this size?
It depends on the signal to noise. So people are, for DES, we cut at 250 arc minutes, right? So roughly 4 degrees. And the survey is 5,000 square degrees. So we don't exploit that at all. But people are thinking about measuring this on 10-degree scales. But that's a bit speculative.
And also to map in the 3D structure mass distribution, do we check the galaxies at different redshift, but the same, more or less the same position in the sky to see the difference between, like, tomographically?
Yes. No, this is done. I mean, if the limit, let's say the lower limit of the correlation function, right? That is determined by something like blending. When are objects actually too close, such that their light is starting to blend, and that then also happens because of atmospheric problems. So you can resolve galaxy pairs that are much closer by in projection if you go to space. But yes, this is done. So the correlation function in DES went from 2.5 arc minutes to 250. We didn't go to smaller scales. We didn't go to larger scales for the reasons that I mentioned. Yeah.
So in this way, we can also map the 3D mass distribution.
Yeah. So the Cosmos survey was exactly designed like that. Cosmos was only 1.6 square degrees, and it had lensing that went much deeper. It had an effective number density of something like 60 galaxies per square arc minute, and that allows you to slice much more finely in redshift. But yeah.
I have a curiosity. If you have the elasticity photometric redshifts 10 times better, what does it do to your weak lensing constraints?
10 times better?
Yeah.
Okay. Now I have to remember these forecasts and how important photo Z errors are. Yeah, but still. So 10 times better, you have probably reached the realm where they are no longer dominant as an error, and so the question is, when do you reach that, right? When do you start caring more about shear calibration than about photo Z's? Maybe it's already...
And what does it do to your constraints?
Yeah, so it's not... So it is not that photo Z errors in the LSST forecasts are so dominant that it would improve them by a lot, right? Even if you take them out entirely, it is not going to be an order of magnitude jump in W. No, it is not, yeah. So there's, yeah, but it is exactly the name of the game to identify what is the most dominant systematic and then beat that down until it is something else and then go in after that. Yeah.
Okay, just a curiosity. When we observe the shear field, the lens data, well, we already observed the data. They already had the shear, but how can we be sure that? I mean, I'm concerned with the how can we say that there is in fact the shear. I mean, how can we? I cannot. Let me rephrase. If I had an unsheared mapping, something like that, and the shear, how can I extract this shear to get into the unsheared mapping without, but we don't observe these?
Okay. Yeah, there is. So, well, let's talk about map making then, right? Because you've probably seen these dark matter maps that were made by reconstructing the kappa field. So kappa is the projected density field, right? You have the density field that's 3D. You project it, you get a 2D field, that's kappa. And reconstructing kappa maps is one thing that DES does and that all the other lensing surveys do, because then you get a map of the dark matter in projection, right? And this reconstruction algorithm is a bit of dark magic art. So there is something that's called the Kaiser-Squires inversion. That's an older technique that has been improved since. But in principle, that's what you would look up to understand how can you invert, how can you go from something that's the shear to something that's actually unsheared. But I can actually show you the relevant equations in the review that I've pointed out. There's the lens equation and the lens matrix that is involved, and I can also show you the Kaiser-Squires inversion algorithm. But this can be done within uncertainties. Yes.
Okay, so I think we should.
I'm sorry, that is very technical, so that's why I'm kind of brushing over this a little bit. But, I'm happy to talk about it over coffee.
Okay, mine is a quick question. So just to clarify, when you take your N of Z, your galaxy distribution, is for your sources?
Yes.
Or your sources, not your lenses?
Okay, so this is important. Two types of lensing. There is, let's say, gamma. This is shear. And this means you correlate, if you have your redshift distribution, Z and dN dZ, and you have 1, you have 2, you have 3, etc. You correlate something that is, so this is source sample only, but your source sample is split into 3 tomographic bins. So you're correlating something that's in here either with something that's also in here or with something that's here or that's here, right? That's what gamma does. But then there is something that's basically position gamma. And so this is cosmic shear, CS, and this is galaxy-galaxy lensing, which is something else. And so here you have not just the source sample, but in addition, you have something that's the lens sample. Different color, perfect. You have something that's the lens sample. And those are sometimes the same galaxies, right? Lots of the lens sample galaxies are also in the source sample, but there's also some others. Usually, so selecting the lens sample is kind of an art. There's different ideas around there. What is a good lens sample? For the source sample, you're trying to get as many galaxies as possible. But for galaxy-galaxy lensing, you correlate the position of something that you take out of this bin with the shape that you take out of that pin. So there is a correlation between the position of a galaxy and the shape of the galaxies that are at a higher redshift. That's galaxy-galaxy lensing, correlation between position and shape. And you have many, many positions and many, many shapes. And this is where you correlate shapes and shapes. Okay. So those are the two different types of lensing. And this is basically a cross-probe of galaxy clustering, which is position-position, right? For galaxy clustering, you correlate the positions of different galaxies. For shear, you correlate the shapes of different galaxies. And then there's this thing in between, galaxy-galaxy lensing, that correlates the position of a foreground thing with shapes of a background thing. Does that make sense? Yeah. And you can imagine that if there is a galaxy, right, there is some preferred orientation, because if there is a galaxy, there is some overdensity, and then there is some preferred orientation as well. Yeah. Oh my God. Okay. Yes, please.
So we know that in the Dark Energy survey, there was a lot of scale cuts and a lot of cuts that are becoming, I think, even a bigger issue as the statistical error bars shrink. So do you think that people will still use DS data for a long time, trying to get in better modeling and better results with the same data? And we can also extrapolate for this LSST. And then there's this more general question: are we getting data too fast? Like with lots of the surveys are getting on like one after the other, and we are not having enough time to really modeling the data that is costing millions of dollars. Should we slow down or not?
Okay, so we should not slow down. That's a wrong message to send to the funding agencies. So it's not good. So let's not do that. But there is one very important message here, which is that only because DES has already analyzed its data, right? It's not done. It's not useless. It is very, very interesting as a PhD project to look into, okay, this is the main DES analysis, but what if I'm now going to include some baryonic physics model and I'm going to push to smaller scales? Or if I include some modeling of galaxy bias that is more speculative, more sophisticated, and I push to smaller scales? What happens if I go to larger scales? What happens if I bin differently in redshift? There's lots of, and the latter one is actually hard. But many people who think, okay, I need to, DES has already done dark energy, DES has already done neutrinos, okay, I have to go some very fancy modified gravity thing. There is great value to just trying to push to different scales, trying to model systematics differently, and those are very, very good PhD projects and very interesting papers to read for all of the DES community. So I can only recommend doing that. And if you are working in DES and if you know, okay, there's a deadline and now we have to do this analysis quickly, you know how many things you cannot do and you wish you could have done. So there is a lot of opportunities for people to go after data that is public. And I think that's undervalued right now. But we should not slow down.
Right. Yeah. So, okay, there are more questions, but please keep your questions for the discussion session. So we'll be back at 4:15 instead of 4, just because, more time for coffee.
Yeah, that's good.
Okay, so let's 17.